Okay, so we had a test last time, and and I wanted to remind you that the paper is due with, let me see, assignment 12 was the assignment due before the exam. Assignment 13 is due, oh, this is Thursday. It's tomorrow. Yeah, we will, it's going to be a very simple one. It's going to be a very short, I think you'll like that this one's not going to be complicated. But then the paper is due with assignment 14, which is due next Tuesday, right? So are there any questions about the paper? Anything that's coming up? I mean, I gave you lots of lead time there, so we still have still have the weekend. Any questions? Are you guys working on it? Okay, we good? Okay, so if there's no questions on the paper, or then today we are going to cover stacks and queues. Now, before we do this, and you guys have probably done stacks and queues in your intro class before, right? So anyway, let's review. A stack. What in, what out? No, wait. The last one that you put in is the first one that you get out. Okay, so that's last in, first out. Well, first in. No, that wouldn't be the same. No, I don't think that would be in. This is the common acronym. Yeah, let's not switch it around. The common way to do this is known as LIFO. Last in, first out. And then the difference between that and a queue is what?
First in, first out?
First in, first out. That's like first come, first served. You know, like you're in the line for tickets. The first one in is the first one who gets the ticket. First in, first. So this is first in, first out, and that's known as FIFO. This stuff actually comes up in finance. You know, you calculate taxes and you sell stock, and but you buy it in more than one time, and there's tax consequences. So which one do you do the capital gains on if you sell a stock? Is it FIFO, LIFO? You know, this has applications all over the place, not just in computing. So anyway, the topic is stacks and queues. Since the original recording of this lecture, we have revised the DP4DS distribution software. Consequently, some of the audio will not match the slides of the video. Figure 7.1 shows the new version of the DP4DS distribution software. We have two new classes now. On the left, we have A stack, which stands for abstract stack, and on the right we have AQ, which stands for abstract queue. Then the subclasses of A stack of the abstract stack are stack A, which is an array implementation of the stack, and then stack L, which is a list implementation of the stack. And similarly, for the queue, we have QA, which is the array implementation of the queue, and QL, which is the list implementation of the queue. So now, the concrete class stack A and stack L both implement the exact same specification for an abstract stack. Namely, there is a constructor, A stack, and then there are the methods isEmpty, isFull, pop and push, top of, and toStream. And similarly, QA and QL now both implement the methods specified for the abstract queue. Namely, we have a constructor AQ, and the operations DQ and NQ, head of, isEmpty, and isFull, and toStream. And so the demos will not exactly match the current implementations of the stacks and the queues. Okay, so the project that we are going to demo, yes, the name of the project is Stack A. So here's the project, Stack A, and when you install that and run it, here's what we get. So check this out, you guys. Stack capacities. It's asking us for the capacity of the stack. So stack A means array. So this is an array implementation of the stack. Are you with me? So we have to say how big it is. So let's just say 4. All right, so that's the capacity. Now the first thing that, now look, we can check, by the way, there's only one stack. We don't have like 5 stacks or anything like that. So what can we check? Empty, full, push, pop, top, right, and quit. So let's see if this stack is empty. E, the stack is empty. F, the stack is not full. Well, that makes sense. And now what we can do, and now how do we, it was what in, what out?
Last in, first out.
Last in, first out. So how do we put stuff in? Push. So P for push. Value to push. By the way, these are reals, 4.4. All right. Now let's write the stack. See what it looks like. So you see we have this little indication from top to bottom. We have 4.4 is in the stack. Now let's push a value to push. Let's say 9.9. All right. So now when we write the stack, you see there's a 9.9 and a 4.4. Are you with me? And notice that 9.9 is at the top of the stack. And now let's push again. Value to push, 2.2. Okay, and let's write this. And by the way, are we empty? Yes or no?
No.
We're not empty. Are we full? Yes or no? What did we say this capacity was? What did we say? We said 4. So we're still not full, right? Now, if we pop, O for pop, what's going to happen? Well, actually, before we pop, let's check to see what the top of the stack is. T for the top. The stack top is 2.2, and if we write the stack, you see the 2.2 is still in there. Are you with me? Now, if we pop, which one comes out? The 2.2 or the 4.4? Well, what was it in? Last in, first out. So O, so value popped is 2.2, so now if we write it, you see the 2.2 was out. Does everybody see how that worked? Okay, and we're still not full. If we push 3.3, are we full yet? No, but if we push 7.7, now are we full? Yes, the stack is full. And if we write this, the 7.7 is on the top of the stack. Is everybody clear? Okay. Now I don't recall, but let's do a little experiment. I think that the main program might not even check if we try to push. I don't remember now if the main program checks to see if the precondition is violated. But you know, we can't. Suppose we want to push. Let's say 2.2. The main program does not check the precondition. Do you see? So our precondition violation statement comes out. It says, precondition violation cannot push onto an empty stack, and we abort it. All right, so end of demo. Okay, so that's the demo. So now let's take a look at the code that does that. So this is an array implementation of the stack, and so you saw that it had the array. We're going to have 2 attributes. The array is, we're going to have an array called underscore data, and by the way, that's our safe array, you know, the one that this code reuse, right? So we are reusing our safe array. And then we have an integer pointer to the top of the stack, which is called underscore top. So underscore data for the array and underscore top for the integer that points to the top of the stack. So here's the code. It's very simple. Check it out. Class stack A doesn't inherit from anything, you know. There's no abstract data types, all that kind of stuff. It's just pretty straightforward. So array T, type T, underscore data, and top is an int. And so there's a constructor. The stack is allocated with a capacity of cap and initialized to be empty. We have bool is empty. Post condition, true is turned if the stack is empty, otherwise false is returned. Is full, just like we would expect. Pop, precondition, this stack is not empty. So, by the way, we tried to push onto a full stack. What would happen if we popped from an empty? You can't, it doesn't have You can't. So that's a precondition violation. So the top value is removed and returned is the post condition. Push, we have the precondition the stack is not full. We demoed that. And then top of, top of is the one that gives us the top without actually removing it. Remember, we demoed that. And then toStream prints out that little message. So here is a picture. Here's in figure 7.2. We have a little snapshot of what underscore data looks like and underscore top. With this one, it looks like, what did the user put for the capacity on this one? Can you tell from the figure? 6. So whatever capacity he puts in, it's indexed from 0. He put in 6, so they're indexed. It's underscore data sub 0 up to underscore data sub 5. So if this is the initial state, part A shows the initial state. Part B shows what happens if you push 3.3. So how do you suppose, what's the code going to be? How do you push onto the stack? What does the code have to do for push?
It's like top gets one more.
Yeah, you got to increase top and then data sub top.
Yeah.
Are you with me? Because top is the integer that's the index of the array. Is everybody clear on that? Yeah.
So I have a question about, like, I guess the usefulness of this, because, like, if we have an array, like, we can already access all the elements that we want to.
Yeah, but you see, that's a good question. Because what is a data structure? A data structure is a way to store and retrieve information. So the reason this is important is because of the way we store and retrieve. So stacks and queues are used in other algorithms. And the way that you store and retrieve with a stack is with push and pop. And the way you store and retrieve with a queue is with, we will see in a minute, is NQ and DQ. So when you need to be able to, when you need to be able to push and pop, it's convenient to build it so that that's the way that you access the data. Because in some applications you need a stack, you need something where you can push and pop. If you didn't have that, if you just had array, then you'd have to say, well, top gets top plus 1, blah, 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 blah. But now it's all encapsulated in this pop. So conceptually, you use it. It's the way you use it.
So it's like the author, like the user doesn't have to know, like, how
doesn't
big
have
the
to
stack
know.
is or anything.
Well, it doesn't have to know what top is.
Right.
You just do push and pop. See? So yeah, that's a good question. This one is such a simple one that but still, those operations, if those operations are what you need in your data structure, and it's quite common. Stacks and queues are all over the place in computing. So they are very useful. Those operations are very useful. Sometimes you need first in, first out. Sometimes you need last in, first out. Okay? So there's push, and then here's what happens if you do a 5.5. So top would go up by 1, and then data sub top would be this. And then here's how you push 4.4. And now here's another thing. What happens if you pop? Let's go back to D. In D, here we're at the top is 4.4. Now what happens, how would you pop? First of all, what do you have to return?
Top. Or like top.
No, data sub top. You have to return data sub top. And then what do you have to do with top?
Decrease it.
Decrease it. But now look in part D. Notice what happens is you decrease it. Now what happened to that 4.4?
It's still there.
It's still there. Why change it? It's garbage. By the way, garbage, the word garbage in programming has a very specific meaning. That's a value that's left over from a previous operation that's going to be overwritten eventually anyway, so therefore it's meaningless. But there's no reason it would be inefficient to make it 0 or to change it. Do you see what I mean? Because look, if the next operation is push 1.1, top's going to go up by 1, and it's going to be the 4.4 is going to be overwritten. So there's no reason to change the 4.4 when you pop. Yeah.
Is there even like, I guess you can make it 0 to like null it out. There's not a way to like null it?
Actually there is not a good, that's a good point, because this is a stack of type T and we don't know what the type T is.
Well, but is there?
So we wouldn't know if we should make it 0.0 if it was a float,
but
or
like
0.
At the same time, like 0 is still a number, but like right now it's just blank. There's not a way to even make it blank. Is there?
There is not way. That is
so
correct.
Regardless, it has to have some sort of number.
Yeah, that's accurate. And in fact, there are garbage values there, and we don't even know what they are. Yeah, that's a good point. Does everybody in on this conversation, okay? Are we good? Okay? So now let's take a look at actually, with that in mind, most of these, they're so simple, they're going to be exercises for the student. Okay? So look, here the constructor is, now what is this called when you have a colon and you postpone the brace until later? That's called a what? Initializer list. In figure 7.2c, is top pointing to the top of the stack, yes or no? Yes. So it's not pointing to where the next one will go when you do the push. It is pointing to the top of the stack. So if top is -1, it's initialized to -1 because the next time you do a push, it will be 0. It will be at sub-0, data sub-0. Is everybody clear on that? So you've got to keep that in mind. Okay? So that's how it's initialized. And then is empty, exercise for the student, but how do you know if it's empty? You got to compare. Oh, you got to compare what with what? Oh, well, yeah. What have you got to look at?
Cap.
No, is it? No, I don't think you look at cap.
Top is -1.
Yeah, you just wrote the code. You just told us the code. Yeah. Okay, and then, but what about is full? Now, what about is full? This is where now how are you going to get access to cap? Now this might be a little tricky. You might not, you're going to have to remember this. What about is full? How are you going to know what the capacity is? We don't have, look, we don't have cap as an attribute. Look, let's go back to our attributes. In figure 7.1. We don't have cap, is all we have is what?
Data.
Underscore data and underscore top. How are we going to know what the, how are we going to?
Okay, you like data.length or something?
Underscore data is is that safe array. Go back to the documentation for that safe array. You will see that we have a method that returns the capacity. So you're going to have to go back and check that out, and that's how you're going to have to get access to the capacity through that data, through that array T. All right. So there's another little hint on how to do that code for the is full. And pop, you know, you're going to have to do, oh, did I do the, I guess I did the precondition for you on this one, for pop. And then push, there's an exercise for the student, but for push, don't forget to do the precondition. Are you with me? Is that good? And top of, here I did, oh, and by the way, I assumed that is empty is written. So that's a nice, handy little way to do that. Just call is empty. I mean, you could test, you could put a test for negative, for underscore top here, but, you know, I think it's more clear to have is empty in the if statement. And then that's an exercise for the student, top of. All right? And then again here in figure 7.4, here is the implementation of the streaming operator. So the streaming operator, you know, stream, is all we do is we call right-hand side dot toStream OS, and OS is the output stream. Okay, so if you take a look at the main program, that message that says top to bottom is printed out in the main program, and what this prints out is just the parentheses and the elements of the array. But now, does it have to go, where does it start? It prints out the left paren, and then it goes from, what did we say it went? From left to right, it went top to bottom. So you see it has to print them out in reverse order, right? For int I gets top, I greater than 0, I minus minus. So anyway, that's a little detail there. Are we good? Is everybody clear? Okay, so that was the stack. Now let's take a look at the queue. And again, we'll do another demo. This time we'll do Q, and again QA is the array implementation. And so let's run this. So the first thing it asks us is for the capacity. Let's make the capacity 4 again. And now this time, what are the operations? Empty, full, NQ, DQ, head, write, and quit. So let's take a look. First of all, let's see if our queue is empty, and it is empty. Let's see if it's full. It's not full. And now this time the operations are NQ and DQ instead of push and pop. So let's do N for NQ. Let's do 4.4. And now let's write. So this time it's from head to tail. All right. And let's NQ another one. And let's do 7.7. And let's write that. So head to tail is 4.4, 7.7. Now let's NQ another one. Let's make it 1.1. Let's write that. And now, now it wants the head of the Q. Now what was the last one that we put in? The last one that we put in was what? Was 1.1. So that person is at the end of the line. Are you with me? And the person is at the front of the line is the first one who came in was 4.4. So if we do H for the head, what comes out? The Q head is 4.4. Are you with me? And now if you, so now is it full? It's not full, so we can NQ another one. So let's NQ 8.8, and let's write this. And now is it full? Ooh, it's full. So we can't put anything in unless we take something out. So now if we DQ, which one's going to come out? 4.4. And so now if we take a look, we got the 7.7 and the 1.1 and the 8.8. And so now we can NQ another one. We can NQ 9.9, and let's write that, and et cetera, et cetera. Is everybody clear on that? So same kind of thing. So let's quit this. That's our demo. Okay, so that's our demo of QA, the array implementation. Now here's the thing, you guys. Because the stack was last in, first out, then top points to the one where you put it in, and top also points to where you take it out from. Are you with me?
Or top.
With the stack, top told us where to put it when we did a push, and it also told us where to pop from when we did a pop.
Yeah.
Are you with me? So, you know, it was like push, we use top, pop, we use top. But now, and why was that? Why could we do that? Because it was what? Last in, first out. Because the last one we push in, first one to take out, top points, you top in both cases. But now what's going to happen? But now, if we use the stack implementation, what's going to happen? Well, now what's going to happen is we're going to put it in, but then where are we going to take it out from? From the head. Boom. So now instead of just the top, so we're going to put in, we're going to NQ, DQ, NQ, NQ, DQ. Do you see? So we need, we don't just need the top. What do we need? Besides an underscore data, which is a safe array of data elements, what do we need? An underscore head and an underscore tail. Are you with me?
Is it more efficient to do it the circular way than to like move everything down to zero?
Yeah, now that is a really good question. What you could do is you could, and you should be able to answer that. The question is it more efficient to do it this way, to make it circular? And the answer, what is your answer to your own question? Yes, because what you could do is when you took it out, when you DQ'd it, you could just in a loop go through and shift everything down. But that's big theta of what? N. Whereas this is big theta of what? 1. Oh, nice analysis. Are you with me? Is everybody clear? Because that loop is big theta of N, yeah. So now the question is, we don't want to shift, you see? So look, so how is that going to work? Well, first of all, let's take a look at the code. So the attributes, now we have an array t underscore data, but now we have int. Now, by the way, this is int. This is not t, right? Because an integer, the index is always an integer. Okay. So int underscore head and underscore tail. So there's QA. There's the constructor, DQ, precondition, the Q is not empty, postcondition, the head value is removed and returned, so that's DQ, and NQ, this Q is not full for the precondition, value is stored at the tail of this Q is the postcondition for NQ, and then we have head of, and then is empty and is full, same as before, and toStream, same as before, right? So now let's take a look at how this is going to happen with the circular Q. So in the beginning, what does it look like? underscore head and underscore tail are initialized to be what does it look like here in this figure 7.6a? 0. And then if we NQ 3.3, then we NQ where? At the...
We're headed.
No, when you get in line, where do you get in line? When you get in line, you get at the end of the line, Buster. You know, you get in at the end of the line, at the tail. So that's the tail of the people at the front are the ones who get served first because they were first come. All right. So NQ 3.3, and by the way, what is tail pointing to? Tail is pointing to where it's going to go, and so at this point, tail does not point to the tail of the queue. It points to what? Where the next one will go when it is NQ'd. Now, is everybody clear on that? Whereas head points to the head of the queue. Is that clear?
Why bother to do it that way?
Well, that's a good question. Let's postpone that for about 2 minutes.
Okay.
And we'll, okay. So now, let's NQ, if we NQ 5, now look, you guys, so what's the sequence of events? Do we increment tail and then put it in at tail, or do we put it in and tail and then increment tail? We put it in at tail and then what? And then increment tail. Is everybody clear? Okay, so that we NQ the 5.5. Let's do another little NQ. So NQ 4.4. Now head, the value of head is 0, and the value of tail in part D is 3. Is that right? Yes. Are you with me? So now what happens if you DQ? When you DQ, you return what head points to the underscore head points to the head of the queue, the element that's in. So you got that's the one you have to return, right? And then you increase head by 1. And now here on this figure, I didn't do it, but the 3.3 is still there. All right, but I don't want to show it because it's going to get confusing if we do. Okay, and so here we NQ 9.9, tail goes up, 9.9 goes in. Now watch this. We NQ 1.1, 1.1 goes up, and now tail is what's the value of tail? 0, 1, 2, 3, 4, 5, right? The value of tail is 5. And now if we DQ, that returns 5.5, and here we are. Now here's the question. At this point, this is another variation. This could be another variation on your comment. If we wanted to increment tail, at this point we could shift the whole thing down by, instead of shifting it down each time, we could shift the whole thing down at this point if we want to NQ something else.
Isn't that still?
It's still big theta of n, but it's not, at least it's not big theta of n on every operation, on every DQ. Mm-hmm. But still it's big theta of n. I've actually seen this, it done that way by people who didn't know any better. Okay, so now what's going to happen is, DQ one more time, and now what happens in part D, in part I, and now what happens if you NQ 7.7? The 7.7 goes at underscore data sub tail, but now what does tail do? Tail gets up to what? It doesn't get up, it goes back to 0. All right, and now if we NQ 6.6, now we are at part K of the figure. Now look at you guys, let's contrast part G of the figure with part K of the figure. You see the difference? The difference is in part G of the figure, the contents of the queue are contiguous in the middle, but in part K of the figure, part of them is on the right-hand side and part of them is on the left-hand side. So what happens is these things keep chasing they keep chasing each other, and eventually, if you NQ and DQ, you'll get back to that situation in part G where they're in the middle. Does everybody see how that works? Okay, so that's a little tricky. So now let's NQ one more. Now here's my question. If we NQ 2.2, then tail is right up next to head. Are you with me? Now here's the point. Do you see at this point the queue is full?
Is it?
That's a good question. Is it?
Well, to be said the
Well, yeah,
Because actually, that's a good question. Maybe because it looks like there's one more space available.
Because when,
But watch this. Yeah, what are you going to say?
well, if it's full when the tail's the same as the head, that also makes
But then it's full. Yeah. We have to consider this to be full, because why? If we didn't, then what would happen is, and we put that there, and tail would be equal to head. But the problem is, when tail is equal to head, that's also when, here, let's go to part G. That's also when it's empty. Because see, if we DQ'd the 5, if starting at point G, if we DQ'd the 5.5 and then DQ'd the 4.4 and DQ'd the 9.9 and DQ'd the 1.1, then where would underscore head be? It would be equal to underscore tail.
But what if you made it so that tail pointed to the actual last element, not the next one, and then when it's equal, then it's full?
Yeah, well, no, you'd have the same problem.
Because like in the beginning, then the tail would be like.
Yes, in the beginning, head would not equal tail.
Yeah.
Yeah, okay.
Yeah, so the condition would be, think it through, and I think you have the same problem. That's how things work. So now let me give you some guidance on how to do this. There's a very common mistake. There's a very valuable guideline for programming the circular cue, and it's this. First of all, you know how mod works. And what's the C++ symbol for mod? Percent. Are you with me? So what happens is, when you increment tail gets tail plus 1. If tail is, let me see, what's the capacity of this cue? In figure 7.6, what's the capacity of the cue?
5.
No, I think the capacity is 6. Sorry, not the capacity of the cue. That's a good point. We have two things. We have the capacity of the cue and the capacity of the what? Of the array T. And what are we saying here? That as far as the user is concerned, the capacity of the cue is actually what? 1 less than the capacity of the array. So whenever the user specifies the capacity of the cue, what the code is going to do is it's going to give an array with what? 1 more. So that as far as the user is concerned, the capacity of the cue is what the user specifies. But the actual array T is going to have 1 more. That's one thing, right? Now look, what happens is when you add 1 to tail, so what's the value of tail in figure 7.6i? 0, 1, 2, 3, 4, it's 5. All right? So now tell me, what is 5 plus 1 mod the capacity of the array? 0. And that's what tail should be. Are you with me? Is everybody clear on that? So here's what you should do. First of all, when you make these tests and when you do these increments, don't do plus plus. Do plus 1 mod the capacity of the array. Are you with me? And never subtract 1. When you do a test, don't test something compared to something minus 1. Always do the comparison with a comparison plus 1 mod the capacity of the array. And then everything will be simple and everything will work. Are you with me on that? So that's just a little programming guideline for how to implement the circular cue. So look in figure 7.7. What's the code for the constructor of a cue? What is the parameter called? What's the parameter for the constructor for the cue? It's cap. That's the cap. That's the capacity of the cue that the user enters. So, but what do we do internally? We do what? Data cap plus 1, and then we initialize underscore head to what? 0, and underscore tail to what? 0. Now, actually they could be initialized to anything. They could be initialized to 1 or to cat minus 1, or, they could be initialized to, as long as it, but, I might as well just initialize them to both to 0. And now that's empty. So what is the condition for them being empty? Is that they are equal. But what's the condition for them being full?
1 or like
Plus 1 mod the capacity of the array. Anyway. Okay. So, so here's the streaming operator. That's just like before. Okay. And then, this time you have to do the toStream. That's an exercise for the student. Okay. So you can do that with a loop. All right. All right. So and then the rest of these, I'm not showing the rest. The rest are just exercises for the student. Are we good? Okay, so that's the array implementation. But now, you guys, here comes an object-oriented design pattern. This is a very simple one. You'll like this. This next pattern is called the adapter design pattern. And I could have brought the book and did a little, hold it up here. It's the Gang of Four. This is a quote from the Gang of Four. Okay. And this is a quote. Adapter allows classes with incompatible interfaces to work together by wrapping its own interface around that of an already existing class. Adapter allows classes with incompatible interfaces to work together by wrapping its own interface around that of an already existing class. So what we're going to do is we're going to do 2 more implementations. We're going to do another implementation of the stack and another implementation of the queue. But these are super simple. Because look, you guys, what do we already have in our library? We have lists. Are you with me? And these lists are already functioning. Do you see? Are you with me? And what can we do with the list? What can we do with the list? We can do what with the list? So how can we add to a list? Do you remember some of those operations of a list? Append, prepend, blah, 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 blah. But now they're called append, they're called prepend, but the user of a stack doesn't want to think in terms of append and prepend. What does the user of the stack want to think in terms of? Pop, push, and pop. So look, with the linked list implementation of the stack wraps its own interface around that of a linked list. You see? And it's all we have. Here's a super simple way to do it. Look, in figure 7.8, here's the code. Now, so this is another implementation, stack L, for the list implementation of the stack. And now look, we don't have an underscore data, and we don't have an underscore top. What do we have? An underscore what? List L. No data, no top, no nothing. We just have a list L. Are you with me? And look, and furthermore, what do we have? We have, now, what is the user going to want with the list? It's going to want a what? It's going to want an is empty. He's going to want a what? He's going to want a pop. He's going to want a push. He's going to want a top of. He's going to want a toStream. Are you with me? He's going to want all that. Yeah.
So to get this stuff then from the list, we would use something similar to what we have in we would use whatever our linked list is, dot the function that we already made in the other one.
Well, yes. But the thing of it is that how do we do the code? So look, here in figure 7.9 is a UML diagram. It's very simple. You see, the user. Do you see up here on the top one? The user. This is our stack L. What does the user of the stack want? He wants is empty. He wants push. He wants pop. He wants top of. He wants toStream. But what does stack L have? Stack L has a what? Has a list L. And what does list L have? All of that stuff. But the user doesn't want to deal with all of that stuff. The user wants to deal with what? Push, pop. But what can we do? How can we implement the push and the pop? We just do it's one-liners. These are all one-liners. Are you with me? So for the constructor, what do we do when the guy wants a new stack? Well, we just do underscore list L gets new list L, type T. All right? And look, when the user wants the stack is empty, what do we return? Underscore list L, arrow what? is empty because that's already written. Are you with me? And look, what do we do? What do we do when the user wants to push? We just do what? List L what? Prepend value. And what do we want to do? Pop. Oh, maybe pop was an exercise for the student.
We did rem last
First.
Wait, rem which?
Fit first.
Was this Q or stack?
No, this is a stack.
Wow. First.
Which is it?
Well, if we're prepending every time.
Oh, prepend.
Well, like-
Is that what we said?
Well-
Wait, yeah. Wait, what was?
It's right
What,
there. It's right
It says
there.
prepend. So if you're prepending.
oh, yeah. Push is prepend. Prepend.
Rem first.
So it would be rem first. Yeah, that's just a one-liner. Rem first. You
But
see?
if you were just appending, you would remove last.
Yeah. Well, so so for a Q, there's also, this is stack L. There's also going to be a what? A QL. And it's all you have to do is do what? Just, I think actually the attribute, a linked list implementation of the Q wraps its own interface around that of the already existing linked list. And so here I'm going to let you do the attribute for that. Okay? But it's all you got to do. It's just like, you see what I'm saying? Only this time I think one of them is going to be prepend. No, rem, well, you figure it out.
Well, I think you can do it either way.
Maybe so.
You'd have to like do the correct removing.
Yeah, maybe you only have to be consistent.
Yeah.
Yeah. Yeah? Yeah. Does everybody see? So I think this, so you got 4 projects that you got to do. You got to do stack A, no, let's see. Stack A, QA, and stack L, and list L. But they're all very, you see, these are all just little one-liners for the wrapper thing. Okay? And this is also, I've actually seen some libraries that I've seen, they have this really complicated list, and they don't even bother to give you a separate wrapper. They just define pop with the list. They just define push and pop with the list, but it's just this one, it's this wrapper idea. They just use the ones that you also have for that data structure. So you can just use it and just restrict yourself to pushing and popping, and it's the same data structure. See? But anyway, this is the wrapper idea. You see how that's convenient, how that works. Yeah? Okay, now there's just, we do have a few more minutes. Let me just show you this. This is a data structure that we're not going to do. I'm not asking you to implement any of this, but I just want to mention it in passing. And I think I've mentioned it before. It's called the priority queue. And let me just mention where the priority queue, an example of where the priority queue could be used. The priority queue is a data structure where you want to always be able to access the highest value. In other words, the value that has the highest priority. That's why it's called a priority queue. Do you see what I mean? So in what data structure do we have where we know where the highest value is? It's a max heap. All right? Because with a max heap, and it doesn't have to be sorted. So we're not sorting. We're not sorting. It's just a heap. We're just maintaining it as a heap. And look, if you look at what these operations are, this what we have is array T is a data, and int is high index. So the array is stored from 0 to high index, but we think of it as a heap. And what happens is one of the operations that we have is extract max. So the precondition is this priority queue is not empty. The postcondition is the maximum value in this priority queue is removed and returned. So how do we do that? We remove it. Yeah, remove it from the top.
But if we're not trying to put the rest of them in order via heap order,
Yeah, then what we have to do is we have to have an insert. The way we build it is by inserting. So we have this new operation called insert that we didn't have before.
and so like if it would be the max, then like it goes.
Well, that's a good question. See, yeah, so here's what happens. Now what happens is we insert into the empty heap, and each time we insert into one more. So now look you guys. It works like this. Now, if we want to insert if we want to insert, and we know this is a max heap, if we want to insert, that means the heap is going to get bigger by 1. We didn't do this before with the heap sort, but it's going to get bigger by 1. So if we insert, where is it going to go? For the heap shape, it's got to go here, right? But now, if we put something here, what do we have to do? We're not putting it here, so we're not sifting down. What are we doing? We're sifting up.
But
Now you remember when we said, you asked me about the sift up. I said, we don't need it for the heap sort. But for the priority queue, you sift up because this might be big. And it sifts up and up and up until it gets to where it either stops or gets to the top.
But I thought we said we're not sorting the rest of them.
We're not sorting. This is
But
not
it's
sorted.
rearranged.
No, well, but it's a heap. It's not sort.
It's rearranging them.
I know, but it's not sorting them.
It's like
This is not a sorted. This is not maintained in sorted. It's maintained as a heap. And when you insert, what happens is you sift up.
So we're not trying to have like them all stay in the order you put them in?
Correct.
Except for the one that's...
Except we want to have access to the biggest one. Do you see? And so I just thought I would show this to you, and you could actually, if you're interested, there's nothing to prevent you from actually installing this and building it and implementing sort up. It's an exercise in the book, but I mean you can experiment with it and do it if you want. It's there for you to play with if you're interested. But it's good for you to have seen that and see this idea at least once, because it's common, but we just don't have time to.
So in a
to do it.
priority queue, the only thing you ever want to be able to remove is the highest value.
Yes, that's a good point.
Yeah.
Thanks for enunciating that. So remember, we said a data structure is a way to store and retrieve values, and a priority queue is the data structure you would use if what you want to extract is the one with the highest priority. Like in an operating system whose jobs have priorities, and you want to have the highest priority job. Yeah? The highest priority job be the one to take it out.
And there are like ways to build it where you can change like what the priority is.
Actually, there is. One of these is increase key. So if you want to increase the priority of this, what you do is you would change its priority, and then do what? And if you increase its priority, then you do what? Sift up. And if you decrease that, you'd sift down. I don't have a decrease. The increase is normally you normally increase the priority of a job, but you could have a decreased priority and sift down.
If you're going to do that, would you have to have each of those things be a certain object that contains both a priority level and then the actual data?
That is a very good point, and the answer is yes. So this would have to be key, and that in fact what you enunciated was the concept of a dictionary with a key value pair, and we're going to do that. We're going to show that's.
Is that like a hash?
Well, that's also related. Hash tables are also related. All right. So good deal. See you next time.